Hello, this is Jude Socrates, and welcome to a portrait of linear algebra. Our video for today has exactly one topic, and it is a method by which we can compute determinants. And that method is called the cofactor expansion. So let me show you the idea. We can see it when we look at the formula for the 3x3 determinant. So we've seen this before, and remember, an easy way to remember this formula is to copy the first two columns to the right and go left to right, top to bottom, and we get the three positive terms. And then you go right to left, going top to bottom also, and you get the three negative contributions. So what I want to show you is we can think about these 6 terms in pairs. So here's what I'm going to do. Let's highlight the entries in the first row. Okay, so we see A11, and there's an A11, and there's the other A11. Okay, so those two together, if you factor out the A11, you'll get A22A33 minus A23A32. Okay, big deal, you might say. A12, there's A12, there's an A23, A31 there, and there's another term there with A12. And this one is also with a minus. So there's a plus and there's a minus. There's a plus and there's a minus. A13, we have A21, A32 plus minus A13, A22, A31. Okay, but where have we seen product of two things minus product of another two things? Oh, that's a 2x2 determinant. Okay, so let's write down what I just said. Okay, let's factor out the A11, and you're left with this pair, A12, this pair, and A13, this pair. Okay, can we think of these pairs as 2x2 determinants? Okay, let's look at the first pair, A22, A33 minus A23, A32. So yeah, you can rewrite it as a 2x2 determinant, but more importantly, where do we see that submatrix? That's right there. 2, 2, 2, 3, 3, 2, 3, 3. Let's go to the third pair. Okay. 2, 1, 3, 2, 2, 2, 3, 1. So this time, 2, 1, 3, 2, 2, 2, 3, 1. That's over there. So those 4 numbers also make up a submatrix. Okay, so what about the middle? 2, 3, 3, 1. 2, 3, 3, 1. Oh, they're not even next to each other, but they are diagonally across each other. Okay, 2, 1, 3, 3. 2, 1, 3, 3. Okay, so you see that there's kind of like a pair there, and there's a pair there, except a determinant is supposed to go this way first, positive, and then this way, negative. Okay, so let's do this. Let's make a copy of the 3x3 determinant, and let's put it here. Okay, we already understand the first and the third. It's the second that's kind of mysterious. Okay, so there it is. I want the pattern to still be left to right plus right to left minus. Okay, I want to keep that pattern because it's easy to remember. 2, 3, 3, 1, 2, 1, 3, 3. Okay, so we said they're over here. There are these 4 numbers over here. So let's bring them together. Okay, so the easiest way to do that is let's erase row 1. They're not involved, except for the A12. Oh, that's actually good to point out. The A12 is right over here. And here are the 4 numbers. Okay, so we're going to do some magic. We are going to delete the top row. Goodbye. And we're going to delete the middle column, which included A12. Still there. Okay, we can still see it. But now we get the 4 numbers right next to each other now, and they're located in the correct place. Okay, so you have 2133, that's over here, so that should have a positive coefficient. 2331, that should have a negative coefficient. Okay, so if I make that true, make that a plus, and make this a minus, then to pay for it, I would need to compensate with a minus sign outside, right? In our algebra. So that's now in the correct order. So of course it would look better if I put the positive term in the beginning. Okay, so there we go. This is now in the correct order, but we pay for it with a minus. Now, before we do the general formula for cofactor expansion, let's do another grouping, okay? So this time, what if I boxed over here? 2, 2, 1, 2, 3, 2, 2, 2, 3, 2, 1, 2. Ooh, what do they all have in common? Those are the terms from column 2. Okay, so who goes with A22? There's the other A22. So I put that over here, and I have A11, A33 minus A13, A31. Okay, so why is that a plus instead of a minus this time? Remember, it was the middle term that had a minus. Why is it now a plus? Well, let's look. A11, A33, right, left to right, minus A13, A31, right to left. Okay, so let's look. Let's do the same thing we did in our last pair. Okay, let's understand this. A22 is right there in the middle. A11, A33, A13, A31 are in the corners. Okay, so how do we bring those 4 numbers together? All right, well, there's A22 over there. We can erase this column, and now A22 is gone, and we can erase this row. Boom. Now those 4 numbers are next to each other in the 2 by 2 determinant formula. Okay, so now let's look at the others, right? Where's A12? I have a plus A23, A31, so plus, okay, so we need a plus A23, A31, so there's a minus in front, okay? So to make that a plus, you need a minus in here. Where's the other A12? Over there. So this one needs a minus A21, A33, minus A21, A33. Okay, so what's going on there? Let's think about A12. Okay, let's make another copy. Okay, A12 is right there. And where are 2133 and 2331? Oh wait, we just talked about that term, okay? And we did say, yeah, we need a minus sign outside so that these 4 are going to be together, and you go left to right, right to left. Okay, great. So we actually already know about that pair. So last pair, A32. Okay, so there's an A32 over there, and I seem to have factored out a minus A32. So therefore, the plus contribution will be this one, plus A11, A23 minus A13, A21. Okay, so we can use the same copy that I made. Let's think about A32. So A32 again is in column 2. And where is A11, A23, A13, A21? Okay, so it's these four numbers. A32 is over here. So erase column 2 and then erase row 3. Boom. Okay, 1, 1, 2, 3 plus 1, 3, 2, 1 minus. That's the way you do it. All right, so here's the general definition that we need. Suppose you have an n by n matrix A. The determinant of the submatrix obtained from A by erasing its ith row and jth column is called the ij minor of A. And we denote it as capital M for minor, M sub ij of A. The ij cofactor of A is the number C sub ij, capital C for cofactor, C sub ij of A equals -1 to the I plus j times the minor mij of A. So what is the meaning of this -1 to the I plus j? I and j are the row and column numbers. So you add them and you have -1 to that power. Okay, well, we know this from calculus, from algebra. If you have a positive exponent, it becomes +1. I'm sorry, if you have an even exponent, it becomes +1. If you have an odd exponent, you have -1. Okay, so where do we get +1? Row 1, column 1, 1 plus 1 is 2. So -1 squared, that's +1. Okay, so if you move to the right or down, you add 1 to the column number or to the row number, but not both. Okay, so you get this checkerboard pattern for this fact, -1 to the I plus j. So this will be a -1, and then if you move to the right one more space, then it will turn even again. 1 plus 3 is 4. Okay, so you will alternate in signs. Okay, so that's why we saw for A12, there was a minus sign taken out. And the same thing happened for A32. Okay, we took out a minus sign. A22 was the positive sign. Okay, so here's a summary of the two ways by which we rewrote the 3x3 determinant formula. So we started out with 3 coefficients from row 1, and we got these corresponding pairs. So this pair over here is the minor M11, and it has a positive contribution, so it's also the coefficient, the cofactor, A11. But this is the minor for A12, and it's 2331 minus 2133. So if you factor out the minus sign, then it becomes a determinant in the right order. So that is the minor M12 for row 1, column 2. And because of the minus sign, that is also the cofactor C12 with the minus sign incorporated into the M12. Okay, and so on for M13 and C13. Let's look at this grouping. So we have column 2 highlighted. So we already know that for A12, there should be a minus outside. But for the A32, there should also be a minus outside. Okay, 1, 1, 2, 3 minus 1, 3, 2, 1. That's the correct submatrix and the determinant in the correct order. So that minor has to be multiplied with a -1 in order to create the corresponding cofactor. Okay, so I know that negative sign is still a little bit confusing, right? So don't worry, we're about to do an example. All right, so here we go. We are going to find the determinant of this matrix, and we're going to combine the use of cofactor expansion with the row operations that we've learned about already. So here's the strategy, my preferred strategy for finding the determinant of a 4x4 or 5x5 matrix. So first look if you can factor out any common factors or a common denominator. Okay, so I deliberately gave you a matrix with a denominator of 6 here. You know what? 9 over 6. I just know this. Let's turn that into 13 over 6. Why not? Okay. So now that cannot be reduced. We'll factor out the 1/6. Okay. Look for a row or column which already has some or lots of zeros. Well, how generous of me. I gave you a single 0. Okay. So we'll either pick column 2 or row 2. Okay. So once you made a choice, produce more zeros on that row or column by using sums. So in other words, type 3 row or column operators. There, now it looks better. Okay. Once you have mostly zeros, except maybe for one entry, then you can perform a cofactor expansion on that row or column. Okay. Now, why are the zeros good? Okay. Well, think about the minor that we get from this 0. Okay. We will delete that column and that row, and we'll get a 3x3 determinant. Okay. But we're going to multiply it by that 0. So why bother? Right? So if the entry is 0, the minor and the cofactor do not contribute at all to the determinant. Okay? And that's why we want to get maybe one entry, which is not 0, in a row or a column. It's too much to ask for all 0. Okay? Then we're going to get a smaller matrix, submatrix. Okay? So from a 4x4, we're going to get hopefully just one 3x3 matrix. And then you can finish off the computation. We just talked about how to do a 3x3, or you could do row operations, or you can repeat this strategy. Okay, so using the same strategy is obviously more important if you're doing like 5x5 or 7x7. Okay, are you actually going to do this by hand in real life? Probably not, because we have computers and software like Maple. All right, when you transfer to a 3-year school, or maybe you're watching it from already like a 4-year college in your 3rd year, you probably are going to use something like MATLAB. Okay, it will do things like this. So compute matrices determinant. Ooh, okay. So 3-digit number, 6-digit number with a negative sign. Okay, so our goal is to get that number, right? So I guess even though there's a 1/6 there, that is still going to give us an integer determinant. Okay, so here we go. Employ this strategy. So first thing we can do is maybe factor out the 1/6. So when we do that, we said that at the end, we need to multiply whatever determinant we get by the 1/6. So I have written that in the past as I owe determinant of A. I owe it 1/6 for what I am about to do. Okay? And that is take the second row and just clear the 6. Times 6. There you go. no more fractions. Okay, so let's make a copy of this one here and copy this. Overwrite the second. All right, so you know what? Let's write the sentence. If I clear the 1/6 from row 2, I will owe determinant of 1/6. Okay. So now, what do we do? Well, what other goodies do we have over here? Check out column 2. 60, 45, 65. We can take out 5. Yeah, that's the best we can do because that's 13 by 5. Okay, so if I factor out the 5 from column 2, I will now owe determinant of A. I owe an extra 5. So I need to put a 5 over there. Okay, so let's do it. Column 2. Divide everybody by 5. And we get that. Okay, so we get new matrix. I will replace column 2 with this. Okay, excellent. So now what? Check that out. So I have a common factor of 3. Okay, common factor of 3 in row 3. All right, so let's copy this. If I factor out the 3 from row 3, I will now owe determinant of A 5/6 times 3, or of course that is simply 5 over 2. Yeah, there we go. Okay, so let's do it. Let's take this, factor out the 3, meaning divide by 3. So we get that. And our new matrix will be, change the third row to this. There we go. Okay, so we still have that single 0 there. And should we pick column 2 or row 2 or something else? You know, you don't have to use that 0 just because it's a gift to you. I think column 2 would be the best choice. Okay, so that 3, we can wipe out the minus 12, make that a 0. And it won't wipe out the minus 13, but it will bring it down to negative 1, right? 4 times 3 is 12, minus 13, negative 1. Now we will have a negative 1 to work with, and we can make that 3, 0. Okay, so think ahead. Okay, when you're making a choice as to which row or column to attack, see, okay, do I have a path forward? Do I have a good path forward? Okay, all right, so now use the 3 in row 3, column 2 to produce, to turn the minus 12 to 0 and the minus 13 to minus 1. Okay, so these are sums, Ooh, look at that. So these are sums. So we do not change the value of the determinant. Okay. So let's do it. We have row 1 plus 4 times row 3. And that will be the new row 1. And then we have row 4 plus 3. 3. No. Also 4. 4 times row 3. So that will give us that minus 1. Okay. So now we will turn the 3 there to a 0. Now use the minus 1 in the new row 4 to turn the 3 into a 0. Okay, so I'm trying to do as much as I can so that when we change the matrix, you'll have as many zeros as we want and a negative 1 in the 4th row. Okay, so now we have the 3rd row, which we haven't changed, and we will add 3 times the 4th row. Okay, so again, this is a type 3, so no change. Alright, so before we scroll down to the next screen, I said to myself, we should label where these came from. Okay, so this came from row 1, this came from row 4, and we produced a new row 4, and it was this new row 4 that we used to clear the 3 from row 3 column 2. So this will be the new row 3 in our next matrix. Okay. Also, we currently owe the determinant of A 5/2. Okay. So let's make a note of that. And I copied our last matrix from here down to here. Okay. So we are going to use that now to make our new matrix. Okay, so this row 1 is going to go over here to replace that row 1. So there we go. And this will replace row 4. Let's take that. Replace row 4. Very good. And this will replace row 3. Excellent. Okay, so as you can see, column 2 is now 3 zeros and a single non-zero entry. Okay, so the next step is going to be crucial. We are going to perform a cofactor expansion on this 4x4 matrix along column 2. Let me write that down. Next, we will perform a cofactor expansion along the second column of this matrix. Okay, so what does that mean? So the zeros will not make any contribution because we are going to delete column 2 in its entirety. And for this 0, we will delete row 1. Okay, that will give us a 3x3 determinant, but it'll get multiplied by 0. So don't bother. Okay, so similarly for that 0 and for that 0. The only thing that will contribute from column 2 will be the negative 1. Okay, so to do the cofactor expansion, we have to think of that checkerboard pattern. Okay, that's a plus, minus, plus, minus, plus. Okay, so the only entry that will contribute is the -1 in column 2, row 4. Okay, so check. 2 plus 4 equals 6. That's even. So the sign is +1. So this term will have a +1 coefficient in the cofactor expansion. Okay, so if you forgot that there should be a plus or minus 1, you would have been lucky if you had forgotten to do that step, because it will be a +1 anyway instead of a -1. Okay, so now we are ready to execute the cofactor expansion. So we account for everything that we have so far. Let us summarize what we need for the determinant thing. We owe this much to the determinant thing. So let's write that as determinant of A equals 5/2 times whatever we will get for the determinant of this matrix. Okay, so we said only the -1 will contribute. Okay, so we will have that -1. And then we are going to create a smaller matrix, a submatrix. Okay, we did say that we had a name for that. Okay, we called it a minor, and we said that will be M42, row 4, column 2. So it will be the determinant of a 3x3 matrix. Okay, so I'm going to take this matrix and we will delete column 2, row 4. Okay, now because these are mostly zeros, it's probably safer to delete row 4 first and then column 2. Okay, not that you forget that row 4 is at the bottom, but let's say if you were deleting row 3 or row 2, it's probably safer to delete that row first. Okay, all right, so we have a 3x3 matrix. Okay, so we need to multiply the answer that we get for that determinant into the final determinant for our matrix A. Okay, so this always makes me nervous when I'm doing this because it's always easy to make a mistake, right? Maybe I put the row in the wrong place, or, I multiplied instead of divided. So here's the original matrix. I made a copy down here. It's just hiding there. And remember that the determinant is -118/380. Okay, so let's check that we have the correct answer. This 3x3 has a determinant this much. Okay, so the correct final determinant for A will be -5/2 times that number. So are we right? Are we right? Thank goodness we are still right. Okay, so I decided, looking at this 3x3 matrix, now that we know we're on the right track, I think what I want to do is check out column 2. There are no zeros anywhere, okay? But I immediately liked that 12 and 11. We can have a 1 here with hardly any effort, okay? So that's my plan. Let's turn this into a 1 by subtracting row 2. Now that we have that 1, we can clear the 11 and the 103. Okay, And then, as bonus, let's do another cofactor expansion based on that one. Okay, so let's execute. Okay, so subtract row 2 from row 1. Here's row 1. Subtract 2. And we get this much. And now, use this new row 1 to clear the 11 and 103 from rows 2 and 3 respectively. Okay, so we have row 2, and we subtract 11 of the new row 1, and we get this much. Ooh, big numbers, but that's okay. We have this row 3, and we subtract 103 of the new row 1. Okay, great. So we have these zeros. This will be the new row 1, the new row 2, and the new row 3. Okay, so let's make the updates. This is where we were. Here's a copy. Here's another copy. So let's now put these new rows where they belong. Okay, so this is the new row 1, and we put that over here. Yes, this is the new row 2, and that goes here. And here is the new row 3, and that goes over here. Excellent. So we have this 3 by 3 matrix. We want its determinant. So now we will get a cofactor expansion along column 2. Okay, so again, we're going to think about the checkerboard pattern. Okay, the only contribution from column 2 will come from that 1. Okay, where is it? Now it's right there. How do we get there? Starting here, plus, now it's minus. Okay, double check. Row 1, column 2, 1 plus 2 is 3, negative 1 cubed, negative 1. Okay, so that 1 will contribute a minus in the cofactor formula. Okay, so I just made a copy of where we are. We want the determinant of A. It is right now 5/2 negative of the minor M42. And our minor, of course, is over here. And we said that this matrix has the same formula, the same determinant rather, as this new matrix, because we only did type 3 row operations, and we didn't exchange the rows around. Okay, so therefore I need the M12 minor of this new matrix. So we need M12 of this matrix. So that should be down here. Okay, where's my subscript? There. Okay, so that would be the determinant of 2 by 2 matrix. Okay, so again, let's make a copy here. And we will erase row 1, column 2. Okay, so we'll erase row 1 first, and those zeros will guide us correctly. That's what we should. Okay, so there you go. The determinant of A is now this. And we said, okay, this M42 is the determinant of this matrix, but there's a minus there. So we need another minus 1. And the good thing, of course, is that they cancel. Okay, so we want negative 1 times M12. Okay, so That's great. We can ignore those two minus signs, and we just need M12. Okay, but M12 is just a 2 by 2 determinant. So we can just use the formula. So we want 343 times negative 8274 minus this product. So that would be a plus 3030 times positive 921. Put that into our calculator. Are we going to get the correct answer? Drum roll, drum roll. Yes, of course. That is the correct final answer. All right, so in summary, this theorem tells us how to apply the cofactor expansion along any row or any column. And we did the clever thing, which was, let's try to make a row or a column with lots of zeros. Okay? Now, if you want to torture yourself and keep the entries as non-zero, that's your business. But how would you adapt the formula? Okay? So now you really have to be aware of what is in the entry that you are erasing. Okay? So you have an n by n matrix to find the determinant of A using a cofactor expansion along row I. Here's what you can do. Okay? Clear a line on your notes and put AI1, AI2 up through AIN. Okay, so write down those numbers, leave space in between them. Okay, and then what do you need? You need the cofactors. So you need the cofactor for I1, the cofactor for I2, and so on, the matching cofactor. Okay, so remember, the matching cofactor includes the sign, the plus or the minus from the checkerboard pattern. Okay, you have to remove row I and column 1. You get a smaller submatrix. You need the determinant of that submatrix. That's your minor. You incorporate the plus or minus 1. That's the cofactor. Okay, so that's why this formula really is practical if everything is 0 except for one term. Okay, I wouldn't bother to use this if you had several non-zero terms. It's just not worth it. Okay, similarly, if you want a cofactor expansion along column J, check it out. A1J, row 1, column J. A2J, all the way through ANJ, the last row. Here are the matching cofactors. So C1J, C2J, up to CNJ. Okay, so again, multiply those together, add them all up, and that's the final answer for our determinant. Okay, and that is our video for today. I hope you enjoyed it. This is Jude Socrates signing off. You will find me on Facebook, and you will find the 4th edition on Facebook and at candlehunt.com. So until our next video, I hope you enjoy the rest of your day.